Welcome back. Although it may not be a welcome back for you if you just came directly from the most recent video. But as you can tell, it's been a few days for me. For one thing, I no longer look like Grizzly Adams. Yay! So let's continue. So in the last set of videos, we were talking about forward rates. So now we're going to talk about the relationship between spot rates and forward rates. So remember, a spot rate is an annual interest rate in effect from time 0 to time t, whereas a forward rate is a rate in effect typically from time t minus 1 to t, but agreed upon today at time 0. Although a forward rate could be from any intermediate time to some other time. So they're related, and basically it's because of arbitrage, that if you know all the spot rates, you can get all the forward rates that are implied by the spot rates, and there's an arbitrage argument for that, and vice versa. So let's dive in. This is one of my favorite parts of the course. It's very intuitive, it's simple, and the only reason there are so many videos for this activity is because it's a longer activity because there's a lot we can do with it. So let's dive right in. So notation-wise, I think I mentioned this earlier in an earlier video, but now we're going to write S sub k in place of S0 of k. It's just more convenient because we're going to be writing a lot of those. So suppose we know the yield curve, or the term structure, for k equals 1 up through n, and we want to find all the 1-year forward rates. We're going to make an arbitrage argument to write an equation relating the yield curve to the forward rate. So the first thing we're going to do is make an interest rate timeline. So you can see this timeline. Given the yield curve and given the desired forward rate, there are two paths we can follow if we invest or buy or sell, say, zero coupon bonds. We can either start at time 0 and just use the n-year spot rate, which will carry us through from time 0 to time n, or we can take this upper path, which uses the n minus first spot rate from time 0 to n minus 1, and then the n minus 1 to n forward rate for the final year. The arbitrage argument, is that these two are going to have to be equal. Let's show why. So arbitrage arguments always have to assume that an investor can do anything they need to do without transaction costs or anything like that. So this means they can borrow or lend along either of these paths. So we're going to look at both types of arbitrage. So first of all, let's suppose that the product of these two growth factors is bigger than the product of the bottom growth factor. If that's the case, then you borrow at this lower rate and use the proceeds from borrowing at time 0 to invest along this higher rate, and then that means because this path gives you a greater return than the bottom path, you have a risk-free profit. Likewise, if the bottom path results in a lower return than the higher path, we just reverse. We borrow along the higher path and then invest along the lower path. So either way, some combination of borrowing and lending will result in arbitrage if one of these is bigger than the other. And if neither are bigger than either, then we have equality. And so we have this natural, intuitive equation right here, although you can't read it when I highlight it like that. But we have this natural intuitive equation, 1 plus s sub n minus 1 to the n minus 1 times 1 plus I0 n minus 1 comma n is equal to 1 plus sn to the nth. That's just equating the different returns along these two pathways. And I think that's really all you got to know, right? And we can solve that equation for I0 n minus 1 n, and then try and memorize those formulas. And if you want to, you're certainly welcome to memorize these. I advise against it because it's so intuitive, and taking up our precious short or long-term memory space with something that we can derive very, very quickly. I don't think it's necessarily the best use of resources, but it depends on your confidence level and your preferences. So just a quick example. We have a yield curve, find the forward rates, right? So there's k equals 1, 2, 3, 4, and 5. So the first thing for k equals 1 if you look at this, we're basically going to have here k minus 1 is 0, so there's nothing here, so we just have this factor on the left, and the right has this factor with k equals 1. You see the 1-year forward rate will always be equal to the 1-year spot rate, or first period forward rate will always be equal to the first period spot rate. Then the next we do a little bit of work. So we just use this equation. I'd like you to pause for a moment and see if you can do this on your own. Okay, I hope you paused. Here are the answers. So as I mentioned, the first are equal, and then we calculate the rest. Right? Not a whole lot to it. I'll let you look at this for a moment. All right, so let's move on. We're going to do another example, but we're going to look at at some graphs of our results for both the term structure and for the forward rates. So we've got two yield curves. We're going to assume they represent annual yields on different classes of zero coupon bonds for K running from 1 to 10. And so occasionally you'll see this. You'll see some little equation for the yield curve instead of just a table, right? In this case, there's a pattern. This first one's linear. Second one is quadratic with a negative leading coefficient. So you know that means it's going to do one of these things. With a negative leading coefficient on a quadratic, your parabola opens downwards from pre-calculus. And what we're asked to do is find the forward rates, and then we're going to plot both. So let's do the first one. So you know this one's linear. And of course, we've got our formula for the forward rates. So for the yield curve, we just plug in the first one, k equals 1, we get 0.091. And then it just goes up by 0.001 each time to 0.092, 0.093, and so on, as you can see in this column. And then we just calculate all of the forward rates. And you'll see the forward rates also go up linearly, starting at 0.91. Of course, the first one always matches, and then going up by 0.02. You could probably work that algebraically, but it's not really that difficult to do these calculations, and it's not terribly time-consuming. So both of these are linear. They're equal at the beginning, and then it looks like the forward rates are higher than the spot rates. And we can see that in this graph. The solid line is the yield curve, the dashed line of the spot rate, or the dashed line of the forward rates. And we actually start here, this part of the graph. I don't know why I let that slide. This part of the graph doesn't exist because we start with at 1. And you see both linear, and the forward rates are a little bit higher. Let's look at the quadratic example. So in typical quadratic, well, this one you can see is the spot rates. If you look, let me give you a moment to just look at these. So the spot rates, you might notice, is growing, but growing at a slower and slower and slower rate, whereas the forward rates are growing at a slower rate, but eventually they hit k equals 7 and they max out and turn around. And as before, we just calculate these, the spot rates using the formula that we were given and the forward rates using our equation. And if we look at the graph, as before, I don't think this part belongs. The first rates are always equal. And you can see that the yield curve has this kind of quadratic shape, like it's approaching its maximum. And the forward rates have this are in the dashed line, and they actually max out here, as we saw on the table, and start to shrink. I'm not sure if there's anything that can be generalized from this. That's something worth thinking about. For example, if your yield curve is always a polynomial function of time, will the forward rates also be a polynomial function and of the same degree? That's one question. Another question for me raised by these graphs are the forward rates always larger than the yield rate, than the spot rates? I'm guessing no. In fact, in this graph, I wonder if you could just find a counterexample by continuing and finding eventually that the spot rates are larger than the forward rates. It looks like it's heading in that direction, but I don't know. These are things to think about. What do you wonder? Think about that. In the next video, we're going to go the other direction. We're going to take forward rates and find the implied yield curve.